today we're going to give you some compelling reasons why you should start thinking about performance in your games and VR experiences. And we're going to show you some of the tech that our team has developed to help you create high-performance games. But first, let me introduce my good friend and colleague, Wouter van Ortmissen. So Wouter has a background in game development. He's worked at Crytek, Maxis, and also at Gearbox on one of my personal favorite games, Borderlands. Wouter taught game programming at the Guildhall. And he's created several open source game engines and languages, my favorite of which is the deliciously named Lobster. Wouter also speaks 6 natural languages, 7 if you include the one he invented when he was a teenager and that only he and his little sister understand. Overall, he's a lovely fellow, and I recommend getting to know him.
All right. Thank you, Jason. So let me introduce Jason to you. So Jason also has a game development background, particularly in animation. Before he joined Google, he was working at Electronic Arts, where his locomotion system was powering the Madden and FIFA franchises. So recently, Jason led our team to create our most recent sample game, Sushi. That's available on the Play Store. We'll see it later. And most importantly, I think that Jason's stated life goal is that he wants to acquire all life's acquired tastes. So I think you should join him in that.
Thanks, Wouter. Wouter and I work on a team called Fun Propulsion Labs at Google. Our mission is to support game developers just like you by creating cross-platform open source technology that you can use in your games. And not just games that you're making now, we also want to ensure that you're set up with the right technology to help you make great games in the near future, too. So today we're going to talk about 3D games and virtual reality.
And why we think they're going to be increasingly large blips on your radar.
Why they're difficult.
And finally, we're going to present some technology that we've created in our team that we think will help you succeed in 3D and VR.
Along the way, we'll show you some of the small sample games that our team has developed to demonstrate our tech. For example, this is Pie Noon. It's a multiplayer standoff game, but with cherry pies. It's pretty serious stuff that we do. But first and quickly, why games? Serious developers make serious apps, don't they?
Well, games are big business. I mean, look at the Play Store. The majority of revenue from the Play Store comes from games.
Yes, and the game market is expanding to new demographics, too. As you can see here, the demographic that likes, say, men screaming with their mouths open, that's pretty well served today. But going forward, new game genres are becoming more and more popular as well. So entire new demographics are going to come online and become game consumers, too.
But maybe they just have their mouths open because they like the candy in the adjacent games?
It is exactly the same face I made this morning when I saw the donuts.
All right. So games make money today, and they're going to make even more money tomorrow. But why do we care about performance? Games are pretty simple, no?
It's true that many of today's games are technically simple. Here's some of my recent favorite games. Does anybody recognize these games? Just call out the names.
Ridiculous Fishing.
Ridiculous Fishing, of course. Anyone else? How about the one in the middle? That's kind of obscure. It's called The Guides. Very odd game worth checking out. And on the right is Pop the Lock. So all of these games have wonderful visual aesthetics, but technically, they don't really tax the hardware.
So games like these should probably still be optimized, for low-end devices or just to save battery. But for the most part, performance is not going to be on the radar for these kind of games. But there are games that do tax the hardware. And as game players get used to these kind of visuals, they're going to be expecting them.
Anyone know this game? That's right, The Wolf Among Us by Telltale Games. So this game was released in 2013 on the Xbox, the PlayStation, Windows, and Mac. And then soon after, it was also released on mobile. So these screenshots are actually from the Android version, and I think they look amazing.
So mobile hardware is getting increasingly powerful. So console game developers are increasingly going to bring these kind of games to mobile.
Yeah.
And that's exactly what they're doing.
Yeah. For example, some of my friends that are still on FIFA Soccer, when they released FIFA 16 this year, they're using a lot of the code that I wrote 3 years ago before I joined Google. And this is code that we really struggled to make run on the consoles at the time. But they just ported over to mobile devices and it runs fine. And in fact, this is something that a lot of console developers really have to do because the mobile game market is growing much faster than the console and the PC game market. So they need to start bringing over these console games to mobile.
And then there's virtual reality, which is intrinsically a 3D experience. So we think that you're going to see more and more of these kind of experiences on mobile pretty soon, and less of the examples that we gave previously.
Of course, there's going to be plenty of both styles of games, 2D, 3D, simple, complex. But still, console games on mobile is going to raise consumer expectations, just like Wouter says. And this means if performance isn't on your radar today, it probably will be in the near future.
So we're going to have to start thinking about performance. But how much do we have to start thinking about performance? What happens when we get it wrong?
Good question. So this game is Tengami. It's a really beautiful, smoothly animated game. The papercraft world in it kind of folds and unfolds like origami as you go through the world. It's strangely calming and kind of zen-like.
So for 3D games like Tengami, you want to ideally hit a fixed frame rate of 30 to 60 frames per second. When you get performance problems, then you're going to drop frames, and that's going to create stuttering. Now, if your game is mostly static without too much motion, you may be able to get away with like a little bit of stuttering. But if you have smooth scrolling, like Tengami has here, or a lot of camera motion, then that stuttering is going to end up being pretty jarring.
And drop frames are even more of a problem in VR. So for cardboard, you want to hit at least 60 frames per second. You might think, well, if I hit 59 frames per second, that's good enough. But in VR, every drop frame is like snagging your eyeball on a rusty nail.
So you're saying that if I hit 59 frames per second, that is like hitting my eyeball on a rusty nail like once per second effectively?
That's exactly how the math works out. So in less dramatic terms, dropping frames means user fatigue and discomfort, and potentially even nausea.
So, and let's not forget about the next billion users. There's like a billion of them after all.
And they're going to have modern phones, but they may not be the fastest phones.
For example, the Nexus 6P and the Android One are both great phones. But just because your game runs great on Nexus 6P is not going to mean it's going to run great on the next billion Android Ones.
And even if you hit 60 frames per second, it's still worthwhile considering performance because wasted CPU cycles mean wasted battery.
And battery is pretty important to mobile game players.
So when you're playing like a simple 2D game and your phone heats up like it's a pocket warmer, that's a good sign that the developer wasn't prioritizing performance.
So you said that mobile is going to become more like a console experience. What does that imply?
Well, let's take a look at how current mobile game development differs from current console game development, and that might give us a sense for where mobile development might go. So first off, mobile development teams are quite small. Console development teams, on the other hand, come in all sizes, some of them quite large. With a small team, you have to limit your technology. But with a big team, your technology stack is going to be correspondingly large.
So to put it in a different way, many of you may be familiar with the idea of like a thin client, thick server model that's very common in web apps and mobile apps. So what you get if you take mobile gaming and you add console-style technology is you get more of a thick client, thick server model where you're doing intensive rendering, physics, animation, all that on the client, and you're still going to have a rich server-side component. So that gets pretty complicated.
Right, okay then. So when we're working with these more technically complicated clients, what are some of the performance problems that we're going to run into?
So let's first talk about memory. Unlike consoles, you don't really have guaranteed amount of memory on a mobile device. And unlike PCs, you don't really have virtual memory either. So what that means is that it really depends on the situation when Android is going to tell you that you've had too much memory. So the only way to make sure that your game fits in memory and stays in memory is use as little as possible of it. And there's another good reason. Memory bandwidth on mobile devices is very low compared to equivalent PC or console devices. So you may see a mobile device and you go like, wow, that thing has like 8 cores in it and stuff. And until you realize that if those 8 cores all start touching memory, then things grind to a halt pretty quickly.
Then there's the thermal consequences of using a lot of resources. Your CPU is going to get throttled. So mobile hardware was designed for apps, which means they're designed to wake up, serve the user, and then idle for a little bit. When it's idling, it gives the CPU some time to dissipate heat. But games, on the other hand, are kind of using the system evenly at all times. So this means that the heat can just kind of build up and build up until the CPU frequency has to be throttled back in order to dissipate it.
And because you don't control this throttling, it kind of has this ping-ponging effect on your frame rate, which is exactly the kind of thing that's going to make your VR users nauseous.
OK, so we need to hit 60 frames per second with no drop frames, especially when targeting VR.
So that's going to be hard to do in C++, and frankly, it's almost impossible in Java.
Now, there's probably some Java programmers in here, so it's probably worth diving into this a little bit. Maybe you can tell us a little bit what performance challenges people see when they develop games in Java.
Well, first, of course, Java has garbage collection. And garbage collection does not help you keep a stable frame rate, because the garbage collector is going to hit at a particular frame, giving you a very lengthy frame, and then another frame is going to be shorter. That's exactly what we don't want. But even besides that, typically Java code is going to be slightly slower than the equivalent C++ code for CPU-intensive stuff, like physics, animation, simulation, that kind of thing. So even if you can make it work, even if you can make it fit somehow, then you're going to end up burning more battery and generating more heat than the equivalent C++. So
it's a really tricky situation. And it's one that's worth considering very carefully, because choosing a language is something you do at the beginning, and optimizing your program for performance is unfortunately something you tend to do at the end. So if you get to the end of your project and you have a lot of trouble squeezing out performance because of the intrinsic nature of your language, well, that's a real sinking feeling.
And of course, with C++, you get this cross-platform nature for free, on mobile and desktop platforms.
And cross-platform is increasingly important as the games become more complicated. So writing your game twice for 2 different platforms in 2 different languages is a very high cost to that. OK, we understand this is challenging. C++ is kind of like a double-barreled shotgun, but with 1,000 barrels, and they're all pointed at your foot.
But that's where our team comes in. We're Fun Propulsion Labs, and we're here to help.
That's our logo, by the way. So what do we do?
So we make C++ game development libraries.
These libraries are cross-platform, so they work on Android, iOS, Windows, Mac, Linux, probably on consoles, but they're not part of our test suite. In some cases, they work on the web, too. They're all open source. They're all on GitHub right now. You can go download them if you like.
And we've created them both for external developers, game developers, and also for internal users at Google.
That's right. They're all independent libraries as well.
So, but let's stop for a second here. Probably people have the question is like, why libraries? Most people will have an existing engine, right?
So from what we've seen, more than half of game developers are actually using a custom engine. So there's a lot of game developers that don't want to buy into monolithic third-party technology. So by providing separate libraries, we allow game developers to adopt our technology piecemeal. They can just use whatever they need and fit it with what they already have. And even if they are using a third-party engine, if there's something out there that they like, they can just grab that and jury-rig it into their engine as well.
Great. So let's talk about these libraries and how they can help you make more efficient games.
OK, excellent. Let's start at the bottom. Wouter, how do we store stuff?
Well, for that, we have flat buffers, which is our serialization library. It works for games, and it works for anything, really. As you all know, serialization is about how we load, store, and encode stuff. And that is very vital for a memory-efficient game. Now, what is special about flat buffers is that it is a format that works equally well on disk and in memory, so you don't actually have to unpack it.
Wow.
Nice one. So this saves on parsing time. It means you don't have any object allocation whatsoever. It generally reduces memory usage, and it is more cache efficient. So what I want to say is if your project, game or not, if it uses JSON or protocol buffers or some other serialization solution, you can probably benefit from using flat buffers.
Let me interrupt there. Interesting fact, that JSON format is so amazing, they named it after me.
That is not true.
It's not true.
But it is a good idea, which is why flat buffers has JSON parsing built in. Right, yes, languages. So we originally designed flat buffers for C++ and game development, but we also have support for your favorite programming language, assuming your favorite programming language is one of C, C++, Java, C#, Go, Python, JavaScript, PHP, Swift, etc. So, and that's just in case that your tools or servers are written in something other than C++.
And sometimes that makes a lot of sense.
Sometimes. So, okay. You know what's also fundamental is all this math that games use. How do we deal with that?
We have a library called Mathfoo, and it implements a lot of common geometry functions, and it's designed to be simple and fast. So, by geometry, we mean the math on vectors and matrices, usually 2, 3, 4 dimensions, sometimes more. Rendering, physics, animation, AI, they all use this kind of math, anything that deals with physical space and calculations within it. Of course, there's other open source math libraries out there, some of them very good, like Eigen and GLM. But we wanted one that was very simple and focused on the math that was required for games and not necessarily, say, for scientific applications, like Eigen is very good at. We also wanted to make a library that was extremely fast, because it's the foundation for all of our other libraries. So we spent a lot of time benchmarking Mathfoo and optimizing it where appropriate. For example, many of the functions use SIMD instructions, especially the matrix operations. So this is like SSE instructions and neon instructions. These leverage the vector processing unit on the chips. So you can get a lot
I think
better.
you're losing the audience, Jason.
Am I really?
Yeah.
Anyways,
Too technical.
It's fast. So we have data and math. Wouter, what do we need next?
So FPL Base is our lowest level game library that we use for rendering, input, loading resources, things like shaders, meshes, textures, anything that you need to get a game on screen, basically. It also has useful functionality for dealing with Android input devices and VR. It also has threaded resource loading. FPL Base was intended as a way to go from like an empty project to drawing something on screen as fast as possible with as little code as possible. So it has all the minimal functionality that you typically don't get when you work on top of raw OpenGL. Now, it's on purpose not meant to be an engine. It's not dictating how your game should be structured or anything like that. It's just meant to be simple and easy and quick to get going. So it works on all platforms, mobile and desktop, thanks to SDL.
SDL is the simple direct media layer.
And other FPL libraries may be used on top of it. So now that we can render things, what's the next thing to make our games come to life?
So animation, I think, is a really great way to bring your games to life.
You would say that.
And Motive is our animation system. It's a really great way to bring character and charm to your games. Animation is kind of intimidating to a lot of developers. There's just a lot of ways to move something from point A to point B. And some of them have a lot of feeling and intent, but others just kind of look robotic. So the goal of Motive is to make it easy to animate everything, smooth and intently. So to do this, we made the runtime extremely fast because often there's a lot in your scene that needs to be animated. It computes values in bulk with the SIMD instructions I was talking about. The memory format is also very compact. And this helps with the memory bandwidth limitations that's intrinsic to mobile devices. With Motive, you can drive animations with pre-authored splines, or you can also drive it procedurally. to say naturally follow a moving target. Okay, so now we're going to show you one of our sample games, Pi Noon, to give you an idea of how simple motion can help bring a game to life. Okay, so most of the animation in Pi Noon is actually procedural. But in our next game, Sushi, we support fully rigged character animation. So the dapper crocodile here will do a little jig when you feed him a piece of sushi, as you would expect. And the jig animation is created using third-party animation authoring tools like Maya or Blender. And it's brought into our game via an animation pipeline that we've written. So we'll show you a video of Sushi in a bit. Okay, Water, so we've got this game animated. How do we communicate with the user?
Well, for that we have FlatUI. So FlatUI is an immediate mode UI library that's meant to make it simple, easy, and efficient to add menus, HUDs, and other elements to your game. So let's talk a little bit about what this immediate mode thing means. It means that rather than constructing your UI using objects and callbacks and things like that, you actually construct a UI by function calls that you create in your UI every frame again. Now that has a whole bunch of advantages. For example, first and all, there's less code. There's less setup work to do, and simple UIs are pretty simple to get going. It's much easier to do a dynamic UI because if you don't call a particular UI snippet, it does not appear on screen. So there's no adding and removing of objects or anything like that needs to happen. It also means that your UI is always consistent with your game state because you basically can't forget to set some state on your UI. Event handling is all local, so it's right there in place when you're constructing your UI and you have the data right there. So there's no callbacks happening that might execute on a different context or something like that. And it's very easy to make custom UI elements because you can just combine multiple function calls into one. For example, here's a contrived example on the slide where we have two UI elements like a label and a button. And as you can see, they're just function calls. The event handling is just an if-then statement. And for the state that we're managing, we can just use any variable that happens to be in scope over here, making it pretty simple. Now, FlatUI has a couple of additional cool features. So first of all, it has very robust font rendering that is Unicode internationalization aware. It generally uses amazingly little memory. Beyond any textures and fonts that you load, it pretty much uses no memory.
That's kind of a theme you're seeing here.
Yeah, exactly. Importantly, it can render things into 3D if you're doing VR, for example. It does automatically out of everything using virtual sizes, which means that your UIs look great on any kind of screen. And it does not dictate a style. If you can render it, it can be your style, basically. So, Jason, you already spoke about animation. What else can you give us that make games come alive?
Well, one of our first libraries, and one of the more popular, is a liquid physics simulator called Liquid Fun. Liquid Fun is a drop-in extension for the popular Box 2D physics engine. It's a really simple way to add 2D liquid, gas, and particle effects to your game. The runtime algorithm is kind of clever, and it's extremely efficient. So you'd probably be surprised at how much complicated motion it can create. One of our other sample games we'll show you here is called Liquid Fun Paint. We'll just show you the beginning of this trailer so you get a sense for what the library does. Okay, so that's the idea. That's a really fun app you can also find in the Play Store. A lot of kids love it.
All right.
Like Wowder.
So our next library is, thanks, Jason. So our next library is Pindrop, which is our audio solution. So what's special about Pindrop is that it goes beyond just mere audio mixing. For example, it handles prioritization and attenuation. That means that if you have a game scene and suddenly there's a lot of events, a lot of gameplay events triggering a lot of sounds, that the system will automatically take care of making that into a coherent audio picture for you, basically. It also allows you to group and selectively override relative importance of whole groups of sounds. For example, if you wanted to make sure that like voiceovers get heard and things like that. Not unimportantly, it's very data-driven, which means that the people that author the audio don't need to do any programming. It's pretty cool.
Corgi is our entity component system. Now, entity component systems have emerged as a popular programming paradigm in games. So they allow you to associate component behaviors with entities in the scene. For example, suppose I could add an animation component to a dog entity, and this would allow the dog to roll over. Or we could add an audio component to the dog, and that would allow the dog to bark. And instead of storing the rollover and barking data with the dog entity, we instead group all the animation data in one spot and all the audio data in another spot. And this allows you to have significantly better memory performance when you're operating on data in bulk, as you have to in games. So note the contrast here between object-oriented programming and component-oriented programming. So the behaviors and the data are stored with the entity in object-oriented programming, right? So entity component systems, there's nothing new. If you're making a game, you probably have your own. So what we've done with Corgi is simply package and document well the one that we wrote and put it up on GitHub for you to use if you like. Corgi, by the way, stands for Component Organized Reusable Game Interface, but mostly we chose the name because of this guy. He's kind of our unofficial project manager on FPL. I mean, you can't say no to those eyes, right?
So SceneLab is our scene editor. SceneLab kind of takes all these previous libraries together. So it uses Corgi for the objects that it edits, uses flat buffers to store all of its data, of course, and it uses FlatUI. The cool thing about SceneLab is that it's so data-driven, so configurable, that if you pass it different kinds of object definitions, it will automatically allow you to edit different things. So it's very easy to kind of slot into a different game and have an editor specifically for that game.
Our last library is called Breadboard. It's an event system that allows you to connect disparate systems using data. So every game has different systems like audio, AI, and the UI. And you want to keep these systems separate so that they don't have to make function calls into each other. Otherwise, you end up with spaghetti code. So Breadboard lets you do this. For example, you could take a footfall event from the animation system and route that over to the audio system, which would then play a stepping sound. And the two systems, they don't need to be connected with function calls. Breadboard also supports some arbitrary logic nodes, so you can route events a little bit more cleverly if you like.
Wow. Look at all those animals.
So you knew this was coming. This is where we take a look at Sushi, our latest game. And in Sushi, you float down a mystic river feeding sushi to well-dressed animal patrons. It's a 3D game. It runs in VR at 60 frames per second. So that's pretty high performance, even though it's like cute characters on the screen and the gameplay is very simple. This is actually technically a high-performance game. And everything in the world is animated. It has a UI, audio, a level editor. So even though it's a very simple game, the technology stack has everything that you would need to make your own high-performance VR or 3D game. And the technology stack in Sushi is the libraries that we just described to you. OK. Cursor go. Uh-oh.
You can do it.
There we go. so all the data in that game is stored in flat buffers. It's edited in SceneLab. And using SceneLab, we can also add Corgi components to all the entities.
And FPL Base is used to render everything and for input and resource loading.
Motive animates all of the motion in the scene.
And FlatUI shows the menus.
Pindrop plays the music and sound effects.
And finally, Breadboard connects all the components together and allows us to define a game flow in data, like Jason said.
OK, it's worth noting that all the sample games that we showed you today are also open source. So you can go to GitHub, download them, and use them to prototype your own ideas. In fact, the social good team here at Google has done just that. This is the team that powers the donations through google.org. And they also drove the newly launched donations card on YouTube. They're doing a lot of good stuff. So what they did with Pi Noon is to create a prototype of their new donations API. This is an API that lets users make in-app donations. And then it'll automatically process the payments and the billing. There's no fees. There's no spam sent to the users. And most importantly, it has the ability for you, the developer, to support any US-based nonprofit. So basically, you're encouraging gamers to support real-world causes from within the game. I think it's a pretty exciting API, and you should check out their work at this link here. And speaking of links,
all right, so if you want to play around with any of the technologies that you've seen so far, this is our developer site.
Yep, all these links and links to all the libraries are in the space for this talk as well. So thanks for listening. We hope you're excited to create high-performance games. And we hope that our technology can help you with that.
So we're going to have a Q&A now. And if you want to talk to me or Jason afterwards, come find us. We're here to help.